Welcome to the Introduction to Battery Technology course. This lecture focuses on Chapter 3, which discusses lead-acid batteries. In this lesson, we'll take a look at lead-acid batteries, one of the oldest and most widely used battery types. They were first invented in 1859 by a French scientist named Gaston Planté, and they were the first rechargeable batteries. Lead-acid batteries remain important today, particularly in vehicles and heavy equipment. But compared to newer batteries, they don't store as much energy for their size and weight. In this lesson, we'll focus on the basics of how they work and the key performance factors you should know when working with them. In this chapter, we'll come across several important terms related to lead-acid batteries. These include lead, performance, capacity, electrolyte, sulfate, failure mode, and corrosion. Among these, let's pause on failure mode. This term describes what happens when a battery can no longer deliver the needed current. For example, in a typical car battery, the positive plate material gradually sheds or flakes off during repeated charging and discharging. Over time, this process weakens the plates until the battery eventually dies. The other terms will also be explained throughout the chapter. However, keep in mind that failure mode is central to understanding why lead-acid batteries wear out and require replacement. Lead-acid batteries are the oldest type of rechargeable battery still in common use, first introduced in 1859. They use lead-based electrodes and a sulfuric acid electrolyte. Despite their age, they remain the most widely used battery type, especially in vehicle starting, lighting, and ignition systems, as well as in backup power supplies and solar power applications. Lead-acid batteries have some clear strengths and weaknesses. On the plus side, they are capable of delivering very high discharge currents, which makes them reliable for applications that require a quick burst of energy, such as starting a car engine. They also have the highest cell voltage among aqueous electrolyte batteries, about 2 volts per cell. On the downside, their biggest limitation is relatively low energy density, only up to around 30 watt-hours per kilogram. This means they are heavier and bulkier compared to newer technologies. Additionally, the traditional flooded type can be hazardous, since punctures may cause leaks of corrosive acid. These trade-offs are crucial to understanding when evaluating the continued usefulness of lead-acid batteries today. This slide introduces the key components of a lead-acid battery. A typical cell consists of 4 main parts: the cathode, made of lead dioxide, PbO2, the anode, made of sponge-like metallic lead, the electrolyte, which is a mixture of sulfuric acid and water, and the separator, a permeable membrane that keeps the electrodes apart while allowing ions to pass through. In the schematic diagram, you can see how these parts are arranged. The cathode and anode are submerged in the electrolyte solution, while the separator prevents direct contact between them, avoiding short circuits. During discharge, electrons flow from the anode to the cathode through the external circuit, powering a connected device. At the same time, ions move through the electrolyte to balance the reaction. Together, these components make the lead-acid battery a reliable source of stored energy, widely used in vehicles and backup power systems. Discharging part 1 of 2. When a lead-acid battery is connected to a load, electrons begin to flow from the anode to the cathode through the external circuit, producing usable electrical energy. At the anode, which is made of metallic lead, a reaction occurs with sulfuric acid to form lead sulfate. At the cathode, lead dioxide reacts with sulfuric acid, hydrogen ions, and the incoming electrons, also forming lead sulfate and water. As this process continues, the sulfuric acid in the electrolyte is gradually consumed. This lowers the concentration of the solution, which in turn increases the internal resistance of the battery and leads to a drop in voltage. If you examine the graph comparing lithium-ion and lead-acid batteries, you can see that the lithium-ion battery maintains a relatively flat voltage during discharge, whereas the lead-acid battery exhibits a steady decline. This highlights one of the key differences in their performance. Discharging 2 halves. Let's read this diagram carefully. During discharge, electrons leave the anode, Pb, travel through the external load R. That's why the arrow shows electrons, E-, moving right, and enter the cathode, PbO2. Inside the electrolyte is almost equal to 36% H2SO4. Sulfate ions move to the plates, and H takes part in the cathode reaction. At the anode, lead reacts with sulfate to form PbSO4 and releases 2 electrons. At the cathode, lead dioxide reacts with H2SO4, H+, and the incoming electrons to form PbSO4 and water. Combine the half reactions and you get the overall discharge reaction. PbO2 plus Pb plus 2H2SO4 2PbSO4 plus 2H2O. The cell delivers about 2.06 V per cell under these conditions. Take a moment to trace the arrow's electron flow outside the cell and ion movement inside, so the chemistry and the circuit picture line up in your mind. Here we see an important fact about lead-acid batteries. According to History of Batteries, lead batteries account for approximately 80% of the total lead production in the United States. This illustrates the widespread and significant impact of lead-acid batteries, not only in energy storage but also in the use of industrial materials. The image here shows a typical example of lead-acid batteries used in everyday applications. When a lead-acid battery is connected to a voltage supply, the charging process begins. Electrons now flow in the opposite direction, moving from the cathode back to the anode. At the anode, lead sulfate is converted back into metallic lead, releasing hydrogen gas. At the cathode, lead sulfate is restored to lead dioxide, releasing oxygen gas. At the same time, the electrolyte regains its strength, reforming into sulfuric acid and water. The graph on this slide shows the charging characteristics of a lead-acid battery. Notice how the charging current starts high and gradually decreases as the battery fills, while the voltage rises and stabilizes. This pattern reflects the chemical reactions reversing during charging. This slide illustrates the charging process of a lead-acid battery, accompanied by its corresponding chemical equation. As the charger applies voltage, the lead sulfate on both plates is converted back into sponge lead at the anode and lead dioxide at the cathode. At the same time, the electrolyte regains its strength, returning to sulfuric acid and water. The chemical equation at the bottom summarizes this process. Take a moment to study the diagram carefully, as it illustrates both the electron flow and the chemical reactions occurring within the cell. Overcharging in a lead-acid battery happens when the battery is pushed beyond full capacity. At this point, no more lead sulfate remains on the electrodes, and instead, water begins to split into hydrogen at the anode and oxygen at the cathode. This process is called electrolysis of water. Overcharging leads to reduced electrolyte volume, lower reaction rates, and even physical damage to the electrodes. In flooded batteries, the gases escape through vents, while in sealed types, the hydrogen and oxygen are recombined into water. The diagram here shows these overcharge reactions in action. Lead-acid batteries come in several types, each designed for specific applications. Common types include SLI or starting, lighting, and ignition batteries SLA, which are sealed lead-acid batteries, VRLA, meaning valve-regulated lead-acid, and AGM or absorbed glass mat batteries. These variations depend on factors such as the additives used, such as calcium or antimony, the thickness of the electrodes, the composition of the electrolyte, and whether the battery is open or sealed. The picture here shows different kinds of batteries, helping us see how labs fit into the wider family of battery technologies. Here we see a calcium-added lead-acid battery, often referred to as a calcium or maintenance-free battery. Instead of antimony, these batteries use a lead-calcium alloy in the grid structure. This change reduces water loss from gassing and lowers the self-discharge rate, which is why they've become the standard in most modern vehicles. The benefits include resistance to corrosion, overcharging, and water usage, as well as higher current output and very low maintenance requirements. However, they also come with trade-offs, specifically shorter overall battery life and weaker performance in extreme temperatures. Their self-discharge rate is moderate, around 1 to 5% per month. In short, calcium batteries are reliable, low maintenance, and widely used, but they are not the best option in harsh temperature environments. Here we see another variation of the lead-acid battery that uses antimony, or SB, as an additive to the lead grid. Antimony helps strengthen the soft lead, making the battery more durable and improving its ability to handle deep discharge cycles. This makes it especially useful for electric vehicles and other applications where the battery undergoes heavy cycling. Batteries with antimony have several advantages. They are less expensive, have stronger electrodes, resist heat, and can recover more easily from a fully discharged state. However, one drawback is that they have a relatively high self-discharge rate compared to calcium-based batteries. The image on the slide reminds us that antimony is a metallic element added to the battery grid to achieve these performance characteristics. SLI, starting, lighting, ignition, batteries. An SLI battery is a lead-acid battery designed to deliver short, powerful bursts of current, mainly to start car engines and power vehicle lights or electronics when the engine is off. These batteries can provide very high current, sometimes around 500 amps, but only for a short period. They are quickly recharged by the vehicle's alternator. The plates inside are thin but have a large surface area, which allows for high current output and high power density. However, SLI batteries are not built for deep energy storage. They typically operate at around 80% of their total capacity and should only be discharged shallowly, about 20%. Their typical life cycle is approximately 500 cycles, meaning they can withstand roughly 500 charge and discharge events under normal use before their performance noticeably declines. Sealed lead-acid batteries, or SLA batteries, are a type of maintenance-free rechargeable battery. They rely on lead plates and a sulfuric acid electrolyte to store and deliver energy. Because they are sealed, they prevent electrolyte loss and can even recombine gases inside the cell, making them safer and easier to handle. Many SLA batteries use a gel electrolyte created by adding silicon dioxide, which further improves safety. They require little to no maintenance and can be operated in almost any position, making them very versatile. However, they must be charged with a low current, and at very high overcharge rates, they cannot fully recombine gases. Overall, SLA batteries are practical, safe, and reliable for a wide range of applications. Now let's take a look at valve-regulated lead-acid, or VRLA batteries. These are a type of sealed lead-acid battery that uses a small valve to safely release internal pressure. Unlike traditional flooded batteries, VRLAs are designed to minimize gas generation during charging. A common subtype is the absorbed glass mat, or AGM battery, which uses a fiberglass mat between the electrodes. This mat holds the electrolyte like a sponge, preventing short circuits and improving resistance to vibration and shock. AGMs also have a lower self-discharge rate, but they come at a higher cost. Overall, VRLA batteries are reliable, maintenance-free, and widely used where sealed, safe, and durable energy storage is required. Take a close look at this diagram. It highlights key structural features, such as terminals, separators, and welded connections, that make VRLA batteries distinct. Lead batteries run on chemical reactions. When the right conditions are not maintained, those reactions cannot happen properly, and the batteries can become permanently damaged. For example, if you discharge a lead-acid battery below 50% of its charge, you increase a chemical process called sulfation. This sulfation builds up on the battery plates, and over time, it will damage the battery and shorten its life. This slide introduces the fabrication of electrodes for lead-acid batteries. There are two main processes. The first is the plant process, which begins with solid lead plates. These plates are immersed in sulfuric acid, and a voltage is applied. This causes a thin layer of lead dioxide to form on the surface. By repeating this process many times, we gradually build up the active material needed for the cathode. The second is the paste process, which starts with lead oxide. The PBO is pressed into a grid made of solid lead, and then voltage is applied. This reduces PBO to metallic lead, creating the porous structure that serves as the anode. The image on this slide shows the internal components of a real battery, including plates, separators, electrolyte, and casing. It helps us connect the fabrication methods to the physical design of an actual battery. This slide highlights several common operational failure modes of lead-acid batteries. First, there is a loss of electrolyte, which can happen during overcharging in flooded batteries or under high charge rates in sealed batteries when valves open due to heat and pressure. Second, electrolyte stratification can occur if the solution is not mixed. In this case, the heavier sulfuric acid sinks to the bottom while water rises to the top. This reduces conductivity and overall performance. Third, distortion of battery plates may occur due to prolonged high-temperature operation or excessive charging. Warped plates can even pierce separators, causing short circuits. Finally, sulfation occurs if the battery remains fully discharged for an extended period. Lead sulfate crystals become stable and cannot break down, reducing the surface area of the electrodes and permanently lowering capacity and performance. These microscopic images show how lead sulfate, or PbSO4, crystals change in size depending on the battery's state of charge. In the early stages, the crystals are very small and fine, which makes them easier to break down during charging. However, as the battery remains discharged for a longer period, the crystals grow larger and more stable. This growth, known as sulfation, reduces the effective surface area of the electrodes, making it harder for the battery to recharge. In other words, the longer a battery remains in a deeply discharged state, the more likely it is to suffer permanent damage. In addition to operational failures, batteries can also fail due to design-related issues. One of the most common is grid corrosion, which occurs when the lead grid is exposed to the electrolyte for an extended period or is subjected to extreme voltages. This type of corrosion is responsible for the majority of lead-acid battery failures, approximately 85% in flooded batteries and around 60% in VRLA batteries, typically appearing near the end of the battery's life. Another issue is the shedding of the active mass. This occurs when the active material paste on the electrodes fails to stick properly to the grid, or when it is damaged by high current or high temperature. When the material sheds off, battery performance drops significantly, and in severe cases, it can lead to a short circuit. Both of these design failure modes underscore the importance of robust materials and stable operating conditions in prolonging battery life. When we charge a lead-acid battery, the voltage gradually increases as the battery is filled with energy. Inside the battery, the lead sulfate on the plates is turning back into lead on one side and lead dioxide on the other side. That's how the battery stores energy again. Once the battery is fully charged, the voltage suddenly jumps higher. That's because the main reaction is done, and now the extra energy starts splitting water into gas. If you examine the graph on this slide, you can see the smooth rise in voltage as the battery charges, followed by a sharp step upward when it reaches 100%. In a lead-acid battery, charging happens in three main stages. The first stage is constant current, also called bulk charging. Here, the current remains steady while the cell voltage gradually increases. This process continues until the battery reaches approximately 80% charge, which typically occurs near 2.4 volts per cell. Next is the constant voltage stage, also known as absorption. At this point, the voltage is held steady, while the current gradually decreases. This stage ensures the remaining 20% of the battery is charged without overheating. Finally, we reach trickle charging, also known as float charging. Lead-acid batteries cannot hold peak voltage for long. To avoid damage, a lower voltage pulse is applied. This keeps the battery topped off, prevents gassing, and avoids sulfation from self-discharge. On the graph, you can see the voltage rising during bulk charging, leveling off during constant voltage, and finally pulsing in trickle charge mode. The dotted line shows voltage, and the solid line shows current. Let's look at what happens during the discharge process of a lead-acid battery. In the first graph, we see how the cell voltage drops gradually as the battery discharges. Once it reaches the end of discharge point, around 1.75 volts per cell, the voltage suddenly falls off very quickly. This sharp bend marks the limit of useful capacity. In the second graph, we see how discharge current affects capacity. At higher discharge currents, the battery's available capacity becomes lower, while at lower currents, the battery can deliver more energy. In simple terms, pulling energy out too quickly reduces the total energy the battery can provide. These two behaviors, when combined, explain why careful control of discharge current and depth of discharge is crucial for both performance and battery life. In a lead-acid battery, the electrolyte consists of sulfuric acid mixed with water, and its concentration changes during both charging and discharging. When the battery discharges, sulfuric acid is consumed and converted into lead sulfate on the plates. As a result, the acid concentration, or what we call specific gravity, gradually decreases. During charging, this process reverses. Lead sulfate is consumed, and sulfuric acid reforms, causing the specific gravity to increase again. Toward the end of charging, the acid concentration can even rise above the starting value, because hydrogen and oxygen gases are released, lowering water content and making the solution more concentrated. The graph here clearly illustrates this process. During discharge, a steady drop in specific gravity is visible, and during charging, the curve rises again as the electrolyte regains its strength. In this slide, we look at the electrolyte behavior in relation to battery voltage and conductivity. The first graph shows that as the battery discharges, the sulfuric acid concentration, or specific gravity, decreases, and with it, the cell voltage also drops. This means the battery's voltage is directly tied to the acid concentration. The second graph highlights conductivity. Specific conductivity reflects how well the electrolyte can carry current. We observe that maximum conductivity occurs at a specific gravity of approximately 1.3 grams per cubic centimeter, which is roughly the midpoint of the capacity range. Beyond this point, conductivity falls off, which also means the internal resistance of the battery changes during both charging and discharging. The state of charge of a lead-acid battery can be estimated by measuring its open circuit voltage. As the battery discharges, the voltage steadily decreases, as shown in the table. For example, a fully charged battery shows about 12.65 volts, while a fully discharged one drops to around 11.89 volts. To measure correctly, the battery should rest for about 48 hours at room temperature, since temperature and electrode additives can affect the voltage reading. As a lead-acid battery discharges, several parameters change together. The electrolyte concentration and specific gravity both decrease, while the open circuit voltage also drops. At the same time, the internal resistance of the battery increases, making it less efficient. This table compares the values of a fully charged and a fully discharged battery, highlighting the direct relationship between performance and state of charge. This slide explains how cycle life in lead-acid batteries depends on both temperature and the depth of discharge. In the first graph, we observe that batteries last longer at lower temperatures, indicating that cycle life increases as temperature decreases. The second graph shows that the effect of discharge depth, shallow cycling, or recharging before the battery is deeply discharged, results in a longer cycle life. In other words, both cooler operation and shallower discharges help extend the overall lifespan of the battery. Self-discharge. Lead-acid batteries lose energy over time even when not in use. This self-discharge occurs because lead and lead dioxide are unstable in sulfuric acid, resulting in slow chemical reactions even when there is no connected load. On average, batteries lose approximately 5% of their capacity per month at room temperature, which is around 20 degrees Celsius. The rate increases at higher temperatures, and older batteries are even more sensitive. The graph here compares new and old batteries, illustrating how self-discharge increases more rapidly as the temperature rises. In this slide about self-discharge, we see how additives like calcium and antimony can reduce self-discharge in lead-acid batteries. The graph compares different cases. Batteries without additives lose capacity faster over time, while those with antimony perform better, and those with calcium perform the best in slowing down self-discharge. This is why modern designs often use these additives to extend storage life. This concludes Chapter 3 of the Introduction to Battery Technology course. For deeper insights, Please refer to the references provided on this page and consult the textbook to further solidify your understanding of the concepts introduced in this chapter. Once you feel confident with the material, you are encouraged to explore the additional resources available in this module, including lecture presentation, recommended YouTube videos, and supplementary readings. These will help you reinforce your knowledge before moving on to the practice exercises and ultimately the end of module assessment.
Thank you. We'll meet again in the next lecture. Thank you. We'll meet again in the next lecture.